Okay, I think I'm recording, so I will um, give you a little update on my debugging process for the collision algorithm. I'm using the impulse-based system as described in your assignment, and we suppose that we have collision. That is, in the code. Um, this is my collision algorithm. Can you see that all right? Um, we've got if and I'm saying for every ball interaction, right? For every pair of billiard balls, um, if the balls collide, so if distance is less than twice the diameter, which is the distance between the centers, right? At the point of collision, um, or soon after the point of would-be collision, right? Because you're going to have a penetration distance, right? And so the first thing we do after we detect a collision is compensate for that. And how do you do that? Well, um, we look, say, we compute the penetration distance where the distance is measured between the centers, right? And so that's in my code here. Um, um, so we want to first compute the collision normal, and so we can figure out, what line we want to move the balls away from each other on. And so this is going to be the collision normal is the vector between their centers, which is the difference in their x positions and their y positions. And I can maybe line this up. That never seems to stay the way I like it, but that's in IntelliSense or something in IDE. Okay, so then we compute the collision vector, maybe, should I call it, not the normal, because we haven't made it of length 1 yet. So the unit normal is not yet, so maybe this should be called the unit normal down here. We're about to compute that. So we compute the magnitude, we compute the unit vector in the direction of the collision normal, and then what I'm doing here, as you can see, is printing everything out because I want to see what's happening to these variables and why is it not behaving properly. So I've got the penetration distance, which is described in our documentation here as being twice the ball radius minus the distance between their centers, right? So that's exactly what this is saying, right? The pen distance is twice the radius minus the distance between their centers. And I want to report, what is that? That should be something slightly less. So that should be a pretty small quantity, right? Because, well, depending on the velocity, right? Okay, so then before moving, I want to know where are these balls, right? And then I want to know um, if why is that indented there? It shouldn't be, right? It must have gotten indented. Um, I can outdent that, and I'm going to move by half the penetration distance um, along the collision normal, right? So this is the magnitude of, well, half that penetration distance because I'm dividing by 2 in the x component and half that in the y component, right? And that should take me to where I want to be. But, the question is, are these the right signs, right? And then we'll talk about where they are after moving and did they move in the right direction. Maybe we should even compute the distance between them at this stage. Um, I also want to compute the relative velocity, and that's what's going on. Right, so this is the collision normal here. Assume that near the time of collision, forces and positions are nearly constant, but there will be a discontinuity in velocities. Yeah. The impulse of collision will push the bodies apart. If the masses are equal, which they are, then the impulse of each ball will be equal in magnitude but opposite in direction. So the question is, are we going in the right direction or the wrong direction, and do we need to check? You know, if let's in fact maybe do that, right? I'm going to say this is where I do the bounce, right? And adding the projection. So I've computed the dot product of the relative velocity with the unit collision normal, and that is the magnitude of the bounce. So I want to multiply the collision normal components by that multiplier, the dot product, and get the projection relative velocity on collision normal. Okay, is it unpaused now? I can't tell. And unpause, is that's kind of a funny button. All right, well maybe, I hope this thing is working properly. All right, so where were we? Right, so we compute the relative velocity. From that we compute the amount of relative velocity that's applied along the collision normal. And the dot product of any normalized vector gives the projection along, which is what we want, right? So you don't have to compute theta, you just have to compute the dot product, right? I guess I should have made that more clear in the statement here, right? Once you have the dot product, you have what you want. Okay, so let's run this and see what's happening with the collision, and maybe from that we can determine what's going wrong. Something's going wrong. All right, so I'm going to hit F5, and notice I've got a little pause here, right? So it's going to pause between each thing. Okay, so here comes the output, and you can see I set up the pool table, and bam, there's the collision, right? And it pauses, right? And it's if you move this out of the way, you can see what's going on here, that the distance has reached a point less than the diameter. The diameter is 40 pixels. And so at that point you can see the collision normal is mostly horizontal and pointed to the left and up. I know it's negative, but negative is up, right, in the y direction. Okay, so you can see in the picture then that the collision normal is pointed from the one ball to the cue ball, which is going back and up, back and to the left. Sorry. So then okay, so now the magnitude, the magnitude of that distance is 39.6, and that's the collision normal, and then so we're going to divide each component by the magnitude and get, this is a vector of length 1. That's the collision unit normal. Oh, okay, I changed that name. And then the penetration distance is about 0.4 pixels here. Is that in pixels, or I think it is, yeah. Okay, so it's not much. Yeah, you can see that that's not much of a penetration, right? Maybe that doesn't even. Oh, can you see what I mean? This is what I mean. It's not much of a penetration. They're just kissing. So let's then say before moving, we can see that the cue ball has these coordinates. These are the oh, sorry, this is the cue ball here, and this is the one ball, right? And And you can see that, they're about 40 pixels apart. And after moving, so this is the compensation for the penetration, we've moved the cue ball to the left slightly, right? And we've moved the and slightly up, right? Decrease the y coordinate a little bit, that's up. Then the one ball has moved slightly to the right and slightly down. That's good, right? That's what we want, given that, they're where they are. Okay, so then the relative velocity, is that accurate? Well, I think what we started out with, if you look at the code, was where's the initial velocity here is the cue ball is the only one that's moving initially, and it's going down and to the right at a speed of square root of 2. That's the magnitude of that vector. And after after a while, it slows down a little bit, right? So after where am I here? After rolling for a while, it's slowed down, right? So instead of being 1 negative, whoa. So the relative velocity, yeah, that's from, so that's to the right and up. Does that make sense that the relative velocity is to the right? I mean, the magnitude looks right, yeah, but should it be to the right and up? That seems actually so yeah, right, because right, sure, the cue ball is going to the right and up at yeah, so and the one ball is not moving, right? Okay, so this is the dot product. The multiplier here is the dot product of the relative velocity, this vector, with the unit normal, this vector. Does that seem about right? So we have like slightly less than this number, say 0.877, and about 20% of this number, which is going to be like 1.5, 1.7, I mean, or 0.17, sorry, so a negative 0.17, so like, yeah, I think that's right. Okay, I don't know. Dot product, is it right that it's negative? Yeah, the unit normal has a negative x component and a positive y component, huh? Okay. Yeah, sorry, I mean the multiply. The dot product, I think let's assume, I mean, it's the math, right? It can't be wrong, can it? So the projection of the relative velocity on the unit collision normal is given by this vector here, and that is pointing down and to the right, mostly to the right, which again kind of makes sense that it's, yeah, just like with the collision unit normal, the y component is the same sign as the x component and about 20% of it. This is also the same sign and about 20%. So that seems right. And so then what we do is we say this is the bounce, and we're going to add this x component of the bounce to the current. See, now this is part of what concerns me here. Why is the x component of the velocity of the cue ball 1.5? How did it get to be that? All right. In fact, let me Well, let's do one bounce, okay? So if I press enter here, oh, enter here, yeah, then I get a whole nother show, and I can actually just capture this. This is sort of the relevant part of that. And I'm going to paste that into my code for further reference and pause. Okay, I think this means I'm recording again if I hit that button. So I went to the code and I added another line just to be sure. You know what as soon as I enter the collision, I want to know how fast is the cue ball going, and when I look to see what that is in the output, indeed you can see the cue ball is going at this speed, which is later computed as the relative velocity, as well it should be, right? Because the other ball isn't moving. Oh, so the further question is, why then is the x component of the velocity here not the same as the x component of the velocity going in? It's like twice as much. The y component of the velocity is also different. So how did the velocity change? We go back to the code and we see, do we ever set the velocity here to anything? Yeah, but if I click on, where is it? Here. That should highlight any place where, yeah, you can, it doesn't highlight very well. I need to change that. So you can see that this is slightly higher, but so I'm not computing them, I'm not assigning anything to the velocity in here, right? I'm just reporting what it is. Here I'm assigning to it, right? But oh, right. So I should report this out before. Okay, I see what I've done. My debugging should come to where I report these things before I change them, right? Then we can see more betterly what's going on. Okay, so I'll try that and then we'll get maybe better debugging information. And I will attempt to. Okay, so now I'm looking at this after doing that. You can see what I should have seen before, which is that the cue ball has its velocity getting larger to the right when it should actually have it subtracted off. And so what I'm going to do is go to the code and have a condition here that if the relative velocity has a negative x component, then we should subtract this thing. Yeah. All right, so I'll work on that. Okay, so I did a couple of things. I added this, if debug mode, which is initially false. Well, I have it set to false here because I don't want to do all this printing stuff. I only want to do that if I need to analyze what's going on. So I changed, where is it? Yeah, here. I changed the sign of these corrections, which I think it's good. It works for this particular situation, but I need to do what I think Mark Alexander said, which is depending upon the relative velocity, perhaps, the sign, positive, negative, is the relative velocity one way or the other, then we're going to want to either add or subtract from these things. And so let me run this, and you can see that I actually speeded up the cue ball a little too, and I haven't tested that yet. So let me see if that doesn't give us something. So here it goes, boom. See, that's a pretty nice hit, right? And boom again. And so as long as the X component of the cue ball is positive, that seems to work out pretty well, although the slowing down maybe needs some work. I don't know what's going on with that, but there you go. Well, to test out my theory, I decided to move the ball. Here's where the cue ball gets set. I moved it, 10 pixels to the left. I had this was plus 20 before. So its initial position is I'll shift it a little bit to the left. So watch what happens now. It'll hit from the other side, and here's the output window. And so it just barely misses, then comes from the other side, and boom! How's that for a nice bank shot? Placing the one ball precisely where I wanted it because I'm an expert snooker booker from... No, I'm not. So, yeah, I've got the other balls in action now. Remember we had commented those out so that they weren't happening, and now they are. I changed the ball number to 4, and so when we run this, what do we see? Just barely misses there. Isn't that a sweet barely miss? And then here it comes, boom. Notice that really the 2 ball doesn't get any impetus, right? But that's a pretty nice interaction there. You see the 1 ball, they're all kind of moving too slow. I know, I'm not sure what to, maybe I just need to increase that friction a little bit, because as it is, it's kind of like playing pool on ice or something. So that collision, yeah. All right, well, I'm overall pretty happy with that. Oh, I mean, that didn't quite make it in the pocket there. All right, well, I'm gonna say that's good for now, and try to post this because I haven't really experimented with this sort of video. So I hope you all having a pleasant hiatus here, and your other classes are going well. Ciao for now.